Hello students, welcome to my second lecture on calculus of residues. In the first lecture, we discussed about some basic definitions on calculus of residues. Now in this lecture, we go through some examples on some problems on poles and residues. See the first problem. Find zeros and poles of the function z plus 1 by z square plus 1 whole square. Let us consider f of z equal to z plus 1 whole square by z square plus 1 whole square. We know that for finding zeros of the function, we equate the denominator to 0. So that is our numerator here, z plus 1 whole square equal to 0. So this means z plus 1 exists 2 times. So from this, z equal to minus 1 and z equal to minus 1. So observe here minus 1 repeated 2 times. So minus 1 is the 0 of f of z with order 2. Now we find poles of the function. We know that for finding poles of f of z, we equate the denominator to 0. So here our denominator is z square plus 1 whole square. So we expand that z square plus 1 whole square and we get z square plus 1 into z square plus 1 equal to 0. So when we simplify or when we find out z values, finally we get z equal to minus z equal to I comma I and minus I comma minus I. So here z equal to I repeated 2 times and minus I is also repeated 2 times. Therefore, z equal to I and z equal to minus I are poles of order 2. Next problem. Find the poles of the function f of z equal to z square by z minus 1 into z minus 2 whole square and residues at each pole. So here we have to find poles of the function and also the corresponding residue at each pole. So the given function is f of z equal to z square by z minus 1 into z minus 2 whole square. To find poles of f of z, we equate the denominator to 0, that is z minus 1 into z minus 2 whole square equal to 0. From this, z equal to 1, comma 2, comma 2. So these are the z values and these are the poles of the function. Now we observe order of the poles. Here z equal to 1 exists one time, so then it is called simple pole, and 2 exists 2 times, that is 2 repeated 2 times. Therefore z equal to 2 is a pole of order 2. Now we have to find residues of f of z at each pole, and we know that how to find residue of a function at a simple pole and also pole of order m by using different formulas. So first, residue of f of z at a simple pole. So we know that formula, residue f of z at z equal to a equal to limit z tends to a z minus a into f of z. So here our simple pole is z equal to 1. So when we substitute z equal to 1 in the formula, we get limit z tends to 1 z minus 1 into z square by z minus 1 into z minus 2 whole square. So this is our f of z in the given problem. And now we replace z tends to 1. We get z, we get residue of the function at a simple pole, that is 1. Now we find out residue of f of z at z equal to 2 is a pole of order 2. So pole of a order 2 means we use the formula pole of order m. So that is residue f of z at z equal to a equal to 1 by m minus 1 factorial into limit z tends to a d power m minus 1 by dz power m minus 1 of z minus a whole power m into f of z. So here our pole is z equal to 2 and our order is m equal to 2. Now we replace z equal to 2 and m equal to 2 in the formula. We get 1 by 2 minus 1 factorial into limit z tends to 2 d power 2 minus 1 by dz power 2 minus 1 of z minus 2 whole square into z square by z minus 1 into z minus 2 whole square. So here we cancel the factor z minus 2 whole square and z minus 2 whole square. Then we substitute. Then we observe remaining function here z square by z minus 1. So observe this is of the form u by v. So here we differentiate one time that function by using u by v formula, and we know that differentiation of u by v, that is u v dash, sorry, v u dash minus u v dash by v square. So when we use that formula here, we get limit z tends to 2, z minus 1 into 2z. So this is v u dash, v u dash minus u v dash by v square. And finally, we replace the limit value, that is z tends to 2. We get it is 4 minus 4 by 1, that is 0. So the residue of f of z at the pole z equal to 2 of order 2 is 0. Next, see the problem 3. Find the residue of z into e power z by z minus 1 whole cube at its poles. Let f of z equal to z into e power z by z minus 1 whole cube. To find poles of f of z, we equate the denominator to 0. That is, here z equal to 1 repeated 3 times, so that z equal to 1 is called pole of order 3. And we know that residue at a pole of order m, that is 1 by m minus 1 factorial into limit z tends to a d power m minus 1 by dz power m minus 1 of z minus a whole power m into f of z. Now we replace z equal to 1 and m equal to 3 in the formula. We get 1 by 3 minus 1 factorial into limit z tends to 1 d power 3 minus 1 by dz power 3 minus 1 z minus 1 whole cube into z into e power z by z minus 1 whole cube. So when we cancel these two terms, we get the remaining function. It is z into e power z. Now we differentiate that function 2 times with respect to z here. So observe here we have multiple of two functions. So we use uv formula, that is differentiation of uv, and we know that differentiation of uv formula, this is differentiation of uv dash plus v u dash. So we use that formula here. We get z into e power z plus e power z. So that is uv dash plus v u dash. So this is the one-time differentiation of the function z into e power z. Now we differentiate one more time with respect to z. We get z into e power z plus e power z. So this is again we use uv formula, that is uv dash plus v u dash e power z into 1, and the last term is e power z. When we differentiate e power z, we get e power z again. Finally, we replace the limit point z tends to 1. We get 1 into e power 1 plus e power 1 plus e power 1. When we simplify that, we get residue of f of z at z equal to 1 is a pole of order 3. So that is 3e by 2. Next problem number 4. Find poles and residues of f of z equal to tan z. So here our function has no numerator. Our function has only numerator. There is no denominator. Now we expand tangent by using sine and cos. We get the denominator and numerator also. So f of z equal to sine z by cos z. For finding poles of the function, we equate the denominator to 0. We get the poles of the function. Those are 2n plus 1 into pi by 2 when n equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. So observe here our poles are all simple poles, and our function form is a different form. It is p of z by q of z form. So here our function is in different form, that is sine z by cos z. So we use the second formula here. So that is residue of f of z when it is of the form f p of z by q of z is p of a by q dash of a. So when we observe our f of z function, so it is of the form p of z by q of z. Here p of z equal to sine z and q of z equal to cos z. Now we find out q dash of z value for replacing q dash of a value. So q dash of z equal to minus sine z, that is differentiation of cos z is minus sine z. Now we find out, now we replace z value, that is 2n plus 1 into pi by 2. Then residue f of z at z equal to 2n plus 1 pi by 2 equal to sine z by minus sine z at z equal to 2n plus 1 into pi by 2. So when we cancel sine z, then we get minus 1. So finally we replace residue, finally we replace z equal to 2n plus 1 into pi by 2. We get residue of f of z at the simple poles z equal to 2n plus 1 into pi by 2. So the next problem, find the residue of f of z equal to 1 minus e power 2z by z power 4 at its poles. So we know that how to find poles of the function. If we equate denominator, we get poles of the function. Here our pole is z equal to 0 and it has order 4. And we know the formula for finding residue of f of z at pole of order m. So this is the formula for finding residue of f of z at pole of order m. And here our pole is z equal to 0 and order is 4. Now we replace z equal to 0 and order m equal to 4 in the formula, we get d power 4 minus 1 by dz power 4 minus 1 z minus 0 whole power 4. When we replace z equal to 0 and m equal to 4, we get limit z tends to 0 d cube by dz cube of 1 minus e power 2z. Now we differentiate this function 3 times with respect to z. So next step, 1 by 3 factorial is a 6, limit z tends to 0. We differentiate one time here. First time we differentiate the function, we get differentiation of 1 is 0 and differentiation of e power ax. We know the formula for differentiation of ax, the differentiation of e power ax, that is d by dx of e power ax equal to a into e power ax. So the formula is differentiation of e power ax equal to a into e power ax. So we use this formula here and our a value is 2. So we get 2 into e power 2z. This is the first time differentiation value. Now we differentiate similarly 2 times. We get minus 8 into e power 2z. Then we replace z tends to 0. We get minus 8 into e power 0. Finally, the residue of f of z at z equal to 0 have pole of is a pole of order 4. We get minus 4 by 3 is the residue. And this is the one more way of finding residue, that is by using Lorentz series expansion, which means negative powers of f of z expansion based on the Lorentz series expansion. Also we can find residue of the function. So we know that the coefficient of 1 by z minus a is called residue of the function. So for finding residue, first we expand the function into series. So that is 1 by z power 4 into 1 minus, we know the expansion of e power x. We use here e power x expansion, that is 1 plus 2z by 1 factorial plus 4z square by 2 factorial plus and so on. Now we apply 1 by z by 4 z power 4. We get 2z by z power 4 plus 2z square by z power 4 plus and so on. When we simplify, we get the coefficient of 1 by z, it is 4 by 3. So based on that, we consider residue. Here our residue of the function is minus 4 by 3. So by using Lorentz series expansion also, we can find the residue of the function. And this is the one more example in the same as previous. So here our function is 1 plus e power z by sin z plus z cos z, but our but our pole is z equal to 0 here. Already they are mentioned the pole of the function, and here we have to find the residue of f of z. So here our pole is z equal to 0. For finding residue of f of z at a simple pole, we use the formula. It is residue f of z at z equal to a equal to p of a by q dash of a. So for finding q dash of a value, first we consider p of z and q of z. So our p of z is 1 plus e power z. When we replace z equal to 0, we get 1 plus e power 0. E power 0 value is 1. So we get p of 0 value is 2. Now we find out q dash of 0 value. For finding q dash of 0 value, first we calculate q dash of z. That is, we differentiate q of z one time. We get cos z plus z into minus sin z plus cos z. Here we use differentiation of UV formula. We get 3 terms. Now we replace z tends to 0 here. We get q dash of 0 value, that is 2. Now we replace finally p of 0 and q dash of 0 here. We get residue of f of z at z equal to 0. So that is 1. So these are the some example problems. You have to try these problems. Thank you.